single slit has a diameter of 0.045 millimeters and is illuminated by monochromatic light whose wavelength we don't know. A screen 1.85 meters away has a central maximum pattern that is 2.10 centimeters wide. So in this pattern, right, we know that this to here, to here is 2.10 centimeters, right? And then we know that there's a screen up here. Let's draw a picture of this. And there's we got a little slit right there. Okay. And this thing is 0.0450 times 10 to the minus third meters, because that's millimeters, right? That is our D. Okay. Now, what they're asking for is what is the wavelength of this light, right? Now notice that, and I'm just going to do, I always do half of this. I don't know why. I don't know that you need to. Okay, but imagine that there's a straight line like this. It goes down and actually hits right there. Okay. That angle right there in radians, okay, in radians, which is the way to do this problem, okay? That angle right there is just the distance divided by the distance to the screen, right? It's the displacement sideways over how far you are away. So that's literally going to be, well, if that's 2.1 centimeters, this is 1.05 centimeters to here, right? That's half of that distance. Okay, so to find that angle, I'm going to go 0.0105 meters is the opposite side, right? And then the adjacent side here is, how far are we away? We're 1.85 meters away. That's this length of this side, 1.85 meters, okay? So let's figure that out. In radians, that is 0.00, and then it's 567 repeating radians. This, by the way, qualifies as a small angle. Do you see that? Right? And an angle like that, anything less than like 1/10 of a radian, we can say is small. Okay, so what that means is we also know that the sine of that angle is equal to lambda over d. Okay, now we could go into radians and go and calculate the sine of the angle, but remember that for small angles, the sine of the angle is approximately the angle. You can try this, and seriously, put your calculator in radians if you don't believe me, and try the sine of 0.001, okay? And it'll, it works pretty well. Okay, so I'm going to say the angle is approximately equal to that. So what I'm going to do is set this thing equal to, so 0.0567 repeating, right? That is equal to, basically it's equal to lambda over d. Right? So 0.00567 is equal to the wavelength that we don't know divided by the diameter of the slit, which we do know. Okay, and that's times 10 to the minus third. Don't forget that. Okay, so literally that number times 0.045 times 10 to the minus third. That gives me the answer I get is that lambda equals 2.55 times 10 to the minus 7th, which of course means that it's also 255 times 10 to the minus 9th, which means it's also 255 nanometers. Now, I know there's some of you that don't like this step. I certainly didn't like that, okay? Like, whoa, can we really do that? Okay, so if you hang on, I'm going to do this legitimately. I'm going to use actual trigonometry. I'm not going to make any approximations, and I'm going to show you that we still get the same answer. Okay, now if you're satisfied with, hey, I got the answer somehow, that's fine. Just hit stop. Okay, but what's going to happen now is I'm going to let's do the thing legitimately. Okay, so we know this distance is 1.85. We know that this distance here is 1.05 centimeters, and that's because it's half of 2.1 centimeters, right? Okay, so let's find Ooh, that's good. That was really good. Okay, let's find that angle. So legitimately that angle is tan minus 1 of 1.05. So I'm going to go 0.0105 divided by 1.85. Okay, I'm gonna do this in degrees. This is gonna be so much more work, and we'll get exactly the same answer, but that's okay. I'm all about that. Okay, so divided by 1.85. That angle is 0.325188 degrees. Okay. Yeah, okay. And then we know legitimately that the sine of that angle, sine of theta, is equal to lambda over d, right? Okay. So the sine of 0.325188 is equal to lambda that we don't know divided by d, which is 0.045. Okay, so I'm going to take that number. I'm going to find the sine of it. Okay, so sine that number times this 0.045 times 10 to the minus third. Now notice, at this point, in the approximation, I was just taking the angle in radians and doing that. But the sine of this will be the same as that angle in radians. Okay, I'm just saying. Okay. And I get, you know what I get? I get that lambda is equal to 2.55 times 10 to the minus 7th meters, which is 255 nanometers. Now, was the other way easier? I just don't know. I don't know. I always do. This was my problem with these as a student, was just, I refused to make some approximation. And I absolutely loathed these problems as a student.